Hello. For this video, we will be talking about integer programming and integer variables. Now, when we talk about linear programming, there are generally two kinds of variables. One is what we call continuous variables, and the other one is called integer variables. Now, what's the biggest difference between the two? Continuous variables, as the name suggests, are variables that can assume any possible value. That's why they're continuous. If you go back to the concept of continuous random variables in your probability class, continuous means that the values of your variables can include decimal values. And the same goes with continuous variables and linear programming. Now, what about integer variables? Integer variables, as the name suggests, are variables that can only contain integer values or whole numbers. And one very special kind of integer variables that we will be eventually using are what we call binary variables. What are binary variables? As the name suggests, binary, or in this case 0, 1, are binary variables are variables that can only contain the values 0 or 1. Essentially, binary variables are like integer variables. So, for example, we let x1 be either 1 or 0, and 1 if, let's say, some variable y is greater than 0, and 0 if y is equal to 0. As you can see, x1 here we've defined to be a binary variable where the value of x1 can either be 1 or 0, 1 if y is greater than 0, and 0 if y is equal to 0. Essentially, x1 is an integer, but we also include the fact that x1 is between 0 and 1. So if you have a constraint that says a variable is between 0 and 1, and that same variable is an integer, then what we are actually defining is what we call binary variables. Now, to introduce you to the use of integer variables, let me give you an example. Let's say you're Coca-Cola Philippines, and let's say you have two bottling centers, or what we call manufacturing centers where you produce Coke. Let's say one is in Laguna, and let's say the other one is in Bacolod. Now, let's say these two manufacturing centers or bottling centers, let's say they produce Coca-Cola products and eventually distribute them to three demand centers. And let's name them Metro Manila, Metro Cebu, and Metro Davao. Okay? Now, according to your operations people, let's say the Laguna Bottling Center can produce 110 units of Coke. And let's say the Bacolod Center can produce 90 units of Coke. On the other hand, according to the marketing department, let's say Metro Manila has a demand of 75 units, Cebu has a demand of 65 units, and Davao has a demand of 60 units. Okay? So these are your demand, and these are your supply. Now, let's say when you deliver goods, or let's say when you deliver your Coke products from Laguna to Metro Manila, the cost to transport these Coke products per unit of Coke is, let's say, 6 pesos. And just to fill up the table, let's say this is 13, and let's say this is 16. And if you're transferring or if you're sending Coca-Cola products from Bacolod to Metro Manila, let's say this is 11, this is 8, and this is 10. So what we have now is a very simple linear programming problem called the transportation problem. And what we'd like to do is we'd like to formulate a linear programming model that uses integer variables in this case. Now, let me place the problem to the upper left corner, and let us now formulate our linear programming model for this transportation problem. To begin with, let us define our variables. we would like to let Xij be equal to the number of units of Coke product, whatever the unit is, produced in manufacturing center I and delivered to demand center J. And in this case, we'd like to define I, our indices, to be 1 and 2, and J to be 1, 2, and 3. Okay? Now, so what is I equals 1 and 2 and J equals 1, 2, and 3? In this problem, we can actually identify or label Laguna to be I equals 1 and Bacolod to be I equals 2, Metro Manila to be J equals 1, Metro Cebu to be equal to J equals 2, and Davao to be equal to J equals 3. Okay? Now, I hope you understand the variables Xij. Xij is the number of units that manufacturing center I equals 1 and 2, to produce and eventually delivered to demand center J equals 1, 2, and 3. So for example, if you want to produce 50 units of Coke in Laguna and deliver it to Metro Manila, then essentially what you are saying is X11 equals 50. Okay? So that is how we try to understand our variables. Now, what about our objective? Our objective, I think, is very obvious. We'd like to minimize our total cost. And what is our total cost function equal to? As you can see, what we have here are the individual cost or the variable cost of sending units from a manufacturing center, I equals 1 and 2, to a demand center, J equals 1, 2, and 3. So these are the 6, 13, 16, 11, 8, and 10. And therefore, we can define our total cost to be 6 X11 plus 13 X12 plus 16 X13 plus 11 X21 plus 8 X22 plus 10 X23. Okay? Or, if you'd like to write this in summation notation, then essentially this is just the double summation of Cij, Xij, for all I and for all j. Now, what is this Cij? We can define Cij, let's define Cij here, to be the cost of delivering from manufacturing center I to, and to be delivered to demand center J. Essentially, this table, this 2 by 3 table is your Cij. Okay? So this is our objective function. Now, what about our constraints? So this is subject to. We technically have 2 constraints. One set of constraints is, we'll talk about the supply constraints, and another set of constraints will talk about the demand constraints. Now let's start with the supply constraints. For your supply constraints, we have X11 plus X12 plus X13 has to be less than or equal to 110. Okay? And X21 plus X22 plus X23 has to be less than or equal to 90. Okay? If you want this written in shortcut form, this is just summation of Xij has to be less than or equal to the supply of I, and you're getting the sum over all demand, and you are restricting the supply for every value of I. Okay? So these are your supply constraints. Now, for your demand constraints, Let me write them here. It should be x11 plus x21 greater than or equal to 75, x12 plus x22 greater than or equal to 65, and then finally x13 plus x23 greater than or equal to 60. Okay? Now, I will leave it up to you to write these constraints in summation form. Okay? You can ask me privately for the answer. What we are now missing are what we call the non-negativity constraints. And to write the non-negativity constraints, we just have to say xij has to be positive. Okay? And because these are Coke products, let us assume we cannot produce a part or a decimal or a fraction of a Coke product, and therefore we need to say xij is greater than 0 and integer. Okay? Well, for all I and j. And this is how we formulate our transportation problem. And what, as you can see, we've used integer variables in this case. Okay? Now, after understanding the concept of integer variables through our previous example, let me now give you an example for binary variables. Let's say we are a matchmaker. We're trying to match 5 girls, so girl 1 until girl 5, and we'd like to match them to 5 boys, boy 1 to boy 5. Okay? What I have here is a grid, a table, a 5 by 5 table, and let us call this the compatibility table. Now, what does this compatibility table show us? It shows us how compatible every pair of girl and boy there is. So, for example, if girl 1 and boy 1 is to be paired or to be matched together, then their compatibility score is a 9. For example, if you pair girl 5 with boy 2, then they don't seem to be very compatible to each other because their compatibility score is a 1. And what we'd like to do is we'd like to come up with 5 pairs, so 5 pairs of girl and boys, that will maximize total compatibility. Now, in order to understand how to formulate this problem into a linear programming model, we need to understand the concept of binary variables. As I previously defined, binary variables are variables where the values can only be either 0 or 1. And we restrict the variables to be 0 or 1 by adding a constraint that says the variable has to be from 0 to 1 and for it to be an integer. Now, how do we use binary variables to formulate this problem? Now, to understand how we will use binary variables, you need to understand how binary variables are like switches, on-off switches. No? If a variable that is binary is equal to 1, it is akin to a switch being turned on. If a variable is equal to 0, then it is also akin to the variable or the switch being turned off. In essence, what we have to do is we have to see in this problem how a switch can be used. Now, imagine girl 1 and boy 1 having an individual switch here. Okay? So disregard 9, and let's say you have a switch here where you can turn on or turn off the switch. And for each cell here, so there are 25 cells, and therefore we have 25 switches. And let's say each switch, if turned on, means that that particular girl and that particular guy will be matched or will be paired together. Okay? Now, if you get that idea, then I will define xij to be a binary variable. So xij is equal to 1 or 0. Binary 1 if girl I is paired with boy J. Okay? So I and J is equal to 1 to 5. Okay? Now, if xij is equal to 0, then we say girl I is not paired with boy J or otherwise. Now, as you can see, we've defined a switch, an on-off switch called xij. And for each pair of boy I and girl J, there is a switch that can turn on and off. And this is how we define it. Now, for our objective, I think it's very obvious that our objective is to maximize our total compatibility. And we'd like to get the total compatibility of all 5 pairings. And how do we get the total compatibility of all 5 pairings? Let me do it this way. Let me write first 9x11 plus 1x12 plus 7x13 plus 5x14 plus 2x15. Now let's focus on this line first. What is 9, 1, 7, 5, and 2? 9, 1, 7, 5, and 2 are the compatibility rating for girl 1 to all 5 boys. Okay? And what does this tell us? This tells us that if we switch on the pairing of girl 1 and boy 1, so that's x11, if we switch this on, then we are adding 9 to our z value, our total compatibility. But if x11 is turned off, or if x11 is equal to 0, then 9 is not added to your total compatibility. So if you look at this entire equation, 9x11 plus x1, x12 plus 7x13 plus 5x14 plus 2x15, this is essentially the compatibility rating that we will get because girl 1 will be paired. And depending on who girl 1 will be paired with, the corresponding compatibility rating will be added. Now, because this is just for girl 1, then we have to add for girl 2. So that is 1 x21 plus 5 x22 plus 8 x23 plus 1 x24 plus 6 x25. So this is your compatibility rating that you will get for girl 2. And we don't want to write everything. And we do the same thing for girl 3, girl 4, until for girl 5. So for girl 5, this is a 9x51 plus 1x52 plus 7x53 plus 8x54 plus 1x55. Okay? Now, I know it's very long. It will contain 25 terms, so from 9x11 until 1x55. However, we can actually write this in a simpler manner using summations. And this is how we write it in summation. This is equal to the double summation for all I and j of Cij, Xij. As you can see, your C's are written here: 9, 1, 7, 5, 2, 1, 5, 8, 1, 6, etc., etc. So we can define Cij to be the compatibility of girl I to boy j. Okay? And therefore, we can write the objective function this way. Double summation all over I and j of Cij, Xij. Now, we do have constraints for this problem. What are the constraints? Well, first, every girl has to be only paired to one guy. And the second set of constraints dictate that every boy will also have to be only paired to a single girl. And how do we write that? For the girls, we write it this way: x11 plus x12 plus x13 plus x14 plus x15 equals 1. This is for girl 1. For girl 2, it's an x21 plus x22 plus x23 plus x24 plus x25 equals 1. And then you can continue on, dot dot dot, until girl 5, x51 plus x52 plus x53 plus x54 plus x55 equals 1. Okay? So what does this tell us? Let's look at this constraint first. x11 is the variable that pairs girl 1 with boy 1. x12, girl 1 with boy 2. x13 is girl 1 with boy 3. x14 is girl 1 with boy 4. And x15, girl 1 with boy 5. Now, eventually, we will be saying xij are binary variables, meaning they can only contain the values 1 and 0. And if you try to understand the constraint here, if you're getting the sum of everything, and each variable here can only be either 1 or 0, and you're restricting the sum to be equal to 1, then what are you saying? What you are saying is that only one of the 5, so x11, x12, x13, x14, and x15, only one of them can be equal to 1. And if one of the variable is 1, then the rest is 0. Which means girl 1 can only be paired with one boy. And each of the other constraints will pertain to the different girls in the group. So this is for girl 1, girl 2, until girl 5. Now, because we practice monogamy, then we also have to have the same set of constraints for the boys. And the constraint will look like this: x11 plus x21 plus x31 plus x41 plus x51 equals 1. As you can see, x11 is girl 1, boy 1. x21 is girl 2, boy 1. Girl 3, boy 1. Girl 4, boy 1. Girl 5, boy 1. And what you're saying here is only one of the switches can be turned on. So writing the constraint for all the other boys, we have x12 plus x22 plus x32 plus x42 plus x52 equals 1 until x15 plus x25 plus x35 plus x45 plus x55 equals 1. Okay? Now, to write this in summation form, we can write this in this way. The summation of xij is equal to 1. Okay? And you're getting, if you look at the equation, in every equation, you're getting the sum of j equals 1, j equals 2, j equals 3, j equals 4, j equals 5. So this is from j equals 1 to 5. And you're writing this constraint for I equals 1, I equals 2, until I equals 5. So this is for I equals 1 to 5. In the same manner, for the constraints for the boys, we have the summation of xij equals 1, and you're getting the sum of i's. So look at this. You have I equals 1, I equals 2, I equals 3, I equals 4, I equals 5. So you're getting the summation over I equals 1 to 5. And you're doing the same thing for j equals 1, j equals 2, until j equals 5. So this is for j equals 1 to 5. And finally, obviously, we have to write xij are binary. Okay? Or, if you want to be technical about it, so or, you write xij is between 1 and 0 and integers for all I and j. So this is also for all I and j. And this is our model for this problem, this matchmaking problem. And this matchmaking problem in general is what we call an assignment model. Why is this called an assignment model? Because essentially we are trying to assign girls or some element here to some element in your column. Okay?